Hey everyone, this is now part 2 of the video on introduction of exponential functions. In part 1, we looked at the graph of the function y equals 2 to the x and then y equals 1/2 to the x. We created a table of values and then we were able to determine the shape of the graph of those two functions by plotting the points on the xy plane. Now, what we are going to do here is to explore those two graphs a little bit further so that we can come up with a more determined conclusion about specific characteristics of exponential functions. Let's go ahead and do that. So here, if you notice, we have the shape of the graph that we derived in video number 1, y equals 2 to the x. Now what we want to do is to be able to discuss some of these peculiarities about this graph. The very first one is this the graph of a function? And I want you to notice that if I were to draw vertical lines, those vertical lines will intersect the graph at only one point. So this is indeed the graph of a function. So I'm going to go ahead and I will say yes, that this is a function. Number 2 is asking here, well, what is the domain of this particular function? I want you to notice that the graph extends to the right of the y-axis, and it also extends all the way to the left of the y-axis. That really means that the domain will consist of all real numbers. So the set of all x such that x is in R becomes the domain of this function. Now, what's the range? Well, I want you to notice that this graph right here is completely above the x-axis. Notice how here on the right, the graph goes all the way to positive infinity. It rises upwards forever. In this particular case, on the left, the graph decreases. It gets extremely close to the x-axis, but it will never cross the x-axis. In fact, if I were to extend the x-axis a little bit further, what is happening here is that the graph will get incredibly close to it, but it will never cross the x-axis. So the graph is always above the x-axis. All the y values are going to be greater than 0. But never equal to 0 because the graph will not cross the x-axis. So the range will be the set of all y such that y is greater than 0, where y is an element of the real numbers. Now, let me elaborate a little bit more on the concept of the graph getting really close to the x-axis. See, there are many graphs that behave like this. And here we have an example. The graph, as x becomes extremely small, as x goes towards negative infinity, see how the graph gets extremely close to the x-axis, like infinitely close to the x-axis, but it never crosses the x-axis. Whenever we have a behavior like this with a horizontal line, then we say that the horizontal line is a horizontal asymptote, That really means that in this particular case, as x goes to negative infinity, as x gets very small negatively, the graph is getting so close to that line, extremely close, but it will never cross, it will never touch the line. So therefore, the x-axis in this case becomes a horizontal asymptote for this function. So I'm going to say that the horizontal asymptote is the line y equals 0. Remember that y equals 0 is the equation of this horizontal line. In this case, the equation of the x-axis. What about x-intercepts? Well, there aren't any x-intercepts. Notice how the graph gets very, very close to the x-axis, but it never touches the x-axis. So therefore, we're going to have to say none. No x-intercepts. Is there a y-intercept? Well, I want you to look. I want you to closely look at this graph. And you're going to notice that, yeah, there is right here. There's only one y-intercept. So I'm going to go ahead and write here 0, 1 as the y-intercept. And then here we have, what's the trend? In other words, is the graph increasing or decreasing? The way that we answer this in mathematics is as follows. You're going to go to your graph and you're going to position yourself on the left part of the graph. So in this case, right here. And then you will pretend that you're going to walk on the graph. So if I'm here and I start walking on that graph from left to right, I'm walking towards the right. Notice how I am now climbing. I'm going up, up, up. So then that means that the graph is increasing. So I'm going to say over here, increasing. Okay. So here we have some of the most important characteristics of a function like y equals 2 to the x. And in this case, I want you to keep in mind how the base is 2, and 2 is a number bigger than 1. All of these things are going to become very relevant in a few minutes. Now here we have the second graph that we explored in the previous video. This is the graph 1/2 to the x. And I want you to notice here that 1/2 is now a number between 0 and 1, so slightly less than 1. And then we can see over here the shape. Okay, so now let's go ahead and look at the characteristics of this graph. So first of all, is this a function? And clearly, yes, it passes the vertical line test. What is the domain? Well, the graph extends all the way to the right of the y-axis and all the way to the left of the y-axis. So the domain consists of all real numbers. The set of all x such that x is in R. Now, what is the range? Same scenario as before. The graph is completely above the x-axis. As x gets very, very large positively, look at the graph. The graph decreases and it gets infinitely close to the x-axis, but it will never cross the x-axis. So that really means that the y values in the range are all greater than 0. Same scenario as before. So the set of all y such that y is greater than 0, where y is a real number. Now, asymptote, same idea. Imagine that I extend the x-axis like this, then the graph is going to keep getting extremely close to the axis, but it will never cross the axis. So again, the x-axis is the horizontal asymptote. We're going to go ahead and state the equation of this horizontal line. And the equation is y equals 0. What is the x-intercepts? Again, the graph never crosses the x-axis, so therefore, none. What's the y-intercept? Notice over here, a single point of intersection with the y-axis. So 0, 1. And what is the trend? If you remember, the trend is talking about, is the graph decreasing or increasing? To answer that question, you position yourself at the very far left, and then you imagine that you start walking on that graph. And as you do that, you will be descending. So then that means that the graph is decreasing. So that's the trend of this particular graph. So now we're going to go ahead and state the definition of this particular function. And notice that I am not calling it a relation anymore. Now I know that 1/2 to the x, 2 to the x, these are actual functions. So a function is called an exponential function if and only if it has the following form. And the form is y equals b to the x. So if a function is expressed in this way as b to the x, it is an exponential function. And I want to emphasize over here that b is the base. And the base is a fixed real number. And then x is now in the exponent, becomes the exponent. And in this case, x can be any real number. All right, so as long as our function has this form, then it becomes exponential. But there are some conditions on the base b. The base cannot be any real number. So we're going to put a comma here. We're going to say comma, where the base must be greater than 0 and the base cannot be 1. So this is extremely important. This is a fixed condition of exponential functions, that the base cannot be any real number. The base must be positive, but it must exclude 1. And it must be positive. That means the base can never be negative. There will be a third video. I'm going to call it for now video 3. And in video 3, I will clearly and carefully explain why these conditions are necessary. For now, in this particular video, we will just accept these conditions on the base as part of the definition. But in video number 3, I will carefully explain why the base must be a number bigger than 0 and why it cannot be 1. In this case now, I have put the two shapes that we got together. And these are both exponentials. So I'm going to say y equals b to the x. Both of these functions have expressions in this form. They both have those expressions. But the bases are slightly different, the conditions on the bases. Remember, in this particular case, the graph is decreasing. Very often, this is referred as exponential decay. And over here on the right, the graph is increasing. So this will be an example of exponential growth. So when do we have exponential decay? When do we have exponential growth? Well, that completely depends on the base. Completely depends on the base. When the base is a value between 0 and 1, like 1/2, 1/3, 0.83, whenever the base is between 0 and 1, we always have exponential decay. And then exponential growth is when the base is greater than 1, strictly greater than 1, like 2. Imagine when you had 2 to the x. If base is 3 or 1.5, as long as the base is bigger than 1, then your exponential function will exhibit growth. That's how you know that. And that's how the base becomes very relevant in determining the trend of the function. Will it be decay, decreasing, or growth, increasing? All right, everyone, I hope that you found this video helpful, and I hope that you feel that now it kind of added to that discussion in video number 1. Please know that I will link video number 1 in the description below so that if you haven't seen it yet, you can easily find it. And then what we're going to do now is we're going to go to video number 3. And in video 3, I will now carefully explain why the conditions on B are necessary. Until next time, everybody. Bye for now.